Recording has started. Welcome everyone who is watching the recording. We're covering sections 5.1 through 5.5, 5.4, not 5.5, excuse me. And we're talking about integration and accumulated change and all that good stuff. So, to start with, is there something in particular that you want to go over? Or should we just kind of start from 5.1 and move our way forward?
We can start from 5.1. I had the most problem in 5.3, but I prefer to go through everything.
Yep. Okay, cool. So we will do a couple problems from 5.1. And we did some Riemann sums, right, in 5.1? So we did the left-handed and right-handed sum?
Yes. Yes.
Okay. I think that's probably the big takeaway from 5.1 in terms of like calculating by hand and understanding how that approximates. I would ask everyone to go to, if you're trying to like get a good idea of what's going on in 5.1, I would say take a look at page 245, figure 5.6. And so this is kind of what we're going to be talking about. We have this curve, and it's like very loosely approximated by these bars under the curve, and then it's much better approximated when the bars are smaller. So we're being more careful, and we're better getting the actual area under the curve. So that, I think, is the big takeaway from 5.1, and we can do some problems to show that. So, let's just do problem 1. So suppose that you travel 30 miles an hour for 2 hours, and 40 miles an hour for a half an hour, and then 20 miles an hour for 4 hours. What is the total distance you've traveled? Sketch a graph of the velocity function of this trip. Represent the total distance traveled on your graph in part B. I would start off actually just by sketching out the graph. Oh, this is, by the way, on page 246. So there's 3 parts. 1, how long did we travel? And then 2, we have this graph of velocity versus time. Okay, so we did 30 miles an hour for 2 hours, so that's 60 miles, plus 40 miles an hour for a half an hour, so that's 20 miles, plus 20 miles an hour for 4 hours, so that's 80 miles. So we traveled 160 miles total. All right. So for our velocity here, we're going to have 40. This can be 20, and this is 0, and then here is 30. And then here will be 10. So I'm just going to block this. This is 1 hour, 2 hours, 3 hours, 4 hours, 5, 6, 7. And I'm going to make the long ones the hour. And then I'm going to put this little dash in here for the half hour. Okay. All right, so basically what I'm going to do is I'm just going to say this is my velocity, and velocity is, this is not talking about distance, this is talking about velocity. So velocity is a function of time, and I'm not talking about, like if I were to have a distance graph, it would look something like it might go up very fast, and I don't actually know, like I didn't really think that graph out. But the point is that the distance graph is always going to be going up because we traveled from 0 miles to 160 miles. And so we were moving forward this entire time. The velocity, on the other hand, is the basically the speed that we were going. And so this is going to look like we traveled 30 miles an hour for 2 hours. So 0 to 1 to 2, we were going 30 miles an hour. I'm actually going to draw this in a different color just to like differentiate it. And then we traveled 40 miles an hour for half an hour. And then we traveled here. We went then 20 miles an hour for 4 hours. So here we are at 2.5, 3.5, 4.5, 5. So that's 1, 2, 3, and then 6.5. So that's 4 hours. Oh, that's 10. Sorry, 20. Idea looks like that. So this graph, I'm going to sketch it over in red just so that it looks a little bit smoother. Go up, go across, we go down, and we go across again. And it's not the most precise thing in the world, but this kind of gets the idea across of what's going on. Okay. Does this make sense? Cool. This is something that they will really like to show you, because do you guys remember what we were talking about when we were like talking about taking like the derivative of a distance traveled? So what is the derivative of distance? If I have a function distance with respect to time, this is going to be equal to what? This is going to actually end up being the velocity. Yes, exactly. So, and then if I have velocity, it's going to be acceleration. So, yeah, exactly. Distance, take the derivative. Get velocity. Take the derivative. Get acceleration. They really like this progression, so you're going to want to get familiar with it. Okay, so that being aside, what are we going to do here? Well, we are going to try to go backwards from velocity to distance, because we know that distance, and we take a derivative, we get velocity. We're trying to do that backwards. And how do we do that? In this case, we're going to find the area under this curve, because it's a pretty straight thing. And so we're going to kind of pretend like there's no, it doesn't look like this, and then he slows down gradually. There's not going to be any curvature here. We're just going to say we accelerate immediately, and this is how it is. So the best way to do this is to block out the different blocks. So this is for 2 hours. This is the first 2 hours. this is actually the next half an hour. And this is the next 4 hours, right? So the area under this chunk is going to be 2 times 30. So that's 60. The area under this chunk is going to be 1/2 times 40. So that's 20. And then the area under this curve is going to be 4, because we're going a distance of 4 hours, times 20. So that's 80. And so the total area under the curve is going to be 160, which matches up with what we have here, which is good. So basically what we did there is we said that, okay, we have velocity. Now we need to go backwards from velocity to distance. How can we do that? Well, this is taking the integral. And the integral has a graphical representation of area under the curve. And just to clarify for some people, I know this confused me, at least when I started doing this. This doesn't have to be curvy. It doesn't have to like look like that. This red thing here, that's a curve. So basically what we're just saying is that, like, what does our graph look like? That's the curve that we're looking at. So we found the area under the curve. We know that because the area under the curve is the integral, and the integral is how we go backwards from velocity to distance, that distance is represented in terms of this on our graph. And we solved the problem. So we've done A, B, and C. So yeah, that is how you do problem 1. And so I think that was a really good, like, foundational problem, just to, like, make sure that you guys understand like the whole process that we're going through, because it's really important to stay on top of what's happening conceptually here. Let's do problem. Let's do problem 3. So we're looking at figure.
Olivia,
Yeah.
I'm sorry. We do the odd problems for problems in class.
Yes, okay. Let's not do problem 3 then. Let's do problem 4.
Okay.
Okay. So a car comes to a stop 6 seconds after the driver applies the brakes. While the brakes are on, the velocities are recorded in table 5.5. Give the lower and upper estimates for the distance the car traveled after the brakes were applied. On a sketch of velocity against time, show the lower and upper estimates given in part A. So I would start here by doing part B and then move on to part A. So we have this graph. We have here's 2, here's 4, and here's 6, and then here's 0. And the velocity is going to be, say that's 100, that would be 50, 5, 75. Okay, so I'm just going to kind of roughly estimate here. So at time 0, velocity is going to be 88, so that's going to be like here-ish. At time equals 2, it's going to be 45. So that's going to be down here. At time is equal to 4, it's going to be 16. And at time equals 6 is going to be 0. So we have a curve that looks like this. And it's just going to equal 0 for the rest of this time. So we're trying to give the upper and lower estimates. So what we're going to do is we're going to do the left-hand sums and we're going to do the right-hand sums. I'm going to draw them both in here. So this is, what is this? This is right. And then, let's do. Can you visualize both of these like this? So I'm gonna, cool. Okay. So clearly the right-hand ones are going to be bigger in this instance. And that's not always the case. If the function looked like this, then the right-hand sums would be, why did I draw it like that? How does one draw a graph? If the graph looked like this, the right-hand sums would be smaller than the left-hand sums. But that's just like the way that you draw, because this is a negative slope, right-hand sums are going to be bigger. So what are we going to do? We're going to find the area under this curve. So this is going to be 2 times 88. This is going to be 2 times 45. And this is going to be 2 times 16. And we're going to add all of these together to get the area. Okay. Let's see if I can get my calculator. Where is it hiding? All right, so I got 298. Oops, wrong color. All right, then we've got the left hand. So the left hand ones are going to be the same process. We're going to say this is 2 times 45 because we go 45 up and 2 across, plus 2 times 16 plus 2 times 0. And so that is going to equal 122, right? Tell me if that's wrong. Cool. So this is the answer for part A. Part A is asking for the upper estimate, and that's going to be 298 feet. And then A is also asking for the lower estimate. And so that's going to be 122 feet. So we know we're going to go somewhere between 122 feet and 298 feet when we hit the break within 6 seconds. So, yeah. Do you understand?
I have a question. So depending on the graph, whether it is increasing or decreasing, the upper and lower estimate is depending on that?
Not the upper and lower estimate, but the right hand.
Yes, sorry.
Yeah, okay. Because we had some confusion last semester where people would like look at a graph that looked like this versus a graph that looks like this, and they would expect the right hand sums to be bigger for both of these. But if you were to find the right hand sums of a graph that looks like this on the bottom, what we would see is we would have one that looks like that, that's across, and then like that. And so these right-hand sums, even though we're going to the right, are not going to be as large as the left-hand sums. I will draw those in blue. So that looks like so the left-hand sums are going to be bigger in this one.
Okay.
So the upper estimate is given here by the left.
Okay. That is more clear now, yeah.
Yeah, so what I'm saying is that right does not equal upper. It depends on the slope of the graph. And you can kind of like, if you sketch it out, you can kind of very easily see, like there's this that has this area that's above the curve, and it's going to go the entire time that the slope is positive. So that's going to be bigger, whichever one has this area above. And then the one that has area below is going to be the smaller one. So I can like fill in this area between the left hand and the curve right now. And so all of this is area that I'm not counting when I'm estimating the size of this curve or the area underneath this curve. So this is very much just estimation.
Okay.
Cool. So that is problem 4. We found our upper estimate and our lower estimate. I just want to reiterate, just to make sure everyone understands, that what this means is that we have this curve that's trying to say exactly how far this car is going to be from the point at which the brakes go on. And so that distance the car is going to travel, so like you slam on the brakes, how far are you going to go? That distance is going to be between 122 and 298 feet. We don't have anything more specific than that right now because we don't know how to find the actual integral. We're just estimating the integral. So all we know is it's between these two numbers. Okay. Let's move on to section 5.2. So we're actually talking about the definite integral here. And personally, this was a really terrifying moment for me when I was learning calculus for the first time, because I had this huge integral symbol, and it was like A and B, and I was like, this is just too much going on. And honestly, it just looked so mathy, it scared me. But I promise it's gonna be fine, because all this means is that what you call those the drawing the boxes underneath the curve is just the Riemann sum. So you just want it area under curve. And you understand how to conceptualize the area underneath the curve, so you can conceptualize the integral. So they have this fancy definition going on in section 5.2 on page 250 that talks about the limits. They say that this is equal to the limit as n goes to infinity of the left-hand sum and as it goes to the right. And what this is saying is basically, remember that graph back on page 245 where we had something that looked like this, and it was approximated in a couple of different ways. We had this one, so it looked like that. So we had this. And so this was more specific than, for instance, this. So this blue one that I'm drawing, there is a bigger distance between point A and point B. So I get more area that is lost in my estimate. Does that make sense? I want to make sure we're on the same page. Cool. Okay. So basically what this is saying is that if I have a graph that looks like this, I want to make the distance between point A and point B approach 0. So I want to make that point converge, and like I'm making like hand gestures. I don't know why I'm doing that because you can't see me. Sorry, I just noticed I was doing that. So I'm trying to make these points converge on one another, where A is going to approximately equal B. So they're getting arbitrarily close. The distance between them is getting very, very small. And so as they do that, the n, the number of points there is, approaches infinity. So that's basically all this formula is saying. It's just saying, imagine you have these boxes, and the boxes get narrower and narrower and narrower, and they just keep getting tiny, and eventually all you've got is a cohesive area underneath the curve, but you can still imagine it in the form of boxes. Okay. So, I don't like this. I don't like these problems. Okay. Let's do problem 7. So use the table to estimate the integral from 0 to 40 of f of x dx. Ooh, let's break down the integral too. So this is the little integral bar. This is what tells you that you have an integral. These tell you it's a definite integral. Later on, you will have the opportunity to work with just this, and so just this with nothing here is indefinite. So when you have a definite integral, you're going from point A to point B. Okay. So then this is your function. And this is necessary. It's just some math mumbo jumbo that's telling you that x is the variable. It's like when you do dx, it's telling you to take the derivative with respect to x. And so that's what you're going to do. If, for instance, you had the function, a function with respect to z, and you were asked to find d dx, you wouldn't be able to do it because there were no x's as the variable. So this is just specifying that x is the variable in this instance. So that's kind of the breakdown of what's going on in an integral. And, oops. Okay, so it's really not that scary once you get used to it. So we have a function, and it is given to us in the form of a table. And what they want us to do is use these sums. It's like killer to go through and do these things by hand once you know that there's a better way to do that. And eventually you guys, I promise, will hit a point where you're like, oh, I can do these in my sleep. But for now, we're going to try to do these by hand, in which they say that this is the limit as n goes to infinity of zero equals 1. So I'm writing it like this because I don't want to rewrite it. So this is basically saying left and right, hand in sums, and then So I just put the left one first, and the right one is kind of in parentheses. And then I have F Ti delta T. Okay, so this, as we know, just basically means add a bunch of things together. That's all this giant Greek symbol means. No reason to worry. Okay, in this case, it's delta x, because x is our variable, not t. So I'm going to change that. And so this is xi. So we're going from 0 to 40. So this whole table is something that we're going to include. And let's get started, I guess. Let's do left first. So that would be, ouch, sorry, my neck. Okay. Basically what we're gonna do is, let's see, sorry, I always like to visualize this better. So this would be f of 0 times, and then our delta x is gonna be 10. Plus f of 10. Oh. Yep. Okay. And then I'm going to go ahead down here and do the right. And that is going to be f of 10 plus f of 20. Okay. Are we following me up to here? So basically what I did was I took this formula and I turned it into this. And basically what we're going to do is we're going to get a long string of numbers. So this is going to give us what looks to be the lower, and this is likely going to give us the upper, but we'd have to check to make sure. So this is going to be, if you want to punch some stuff into the calculator with me, sorry, my calculator is ridiculous. Oh, cool. Wow, you did that really fast. Okay, so this one is going to be 16,450, and this one is going to be 17,550. Okay, so basically what this is saying is that this is going to be somewhere between the integral, here I'll rewrite it over here, the integral from 0 to 40 of f of x is equal to somewhere between 16,450 and 17,550. At this point, we are using sums to find out what it is. So this is the What did you say about 17,000?
That's what the average is gonna be, right?
Yeah. Okay.
Yeah.
Yeah. If we wanted a single number, we would average it. So we would say 17,000. But I just want to like make sure that everyone knows that this is all that we can definitively say. We know this is true. This is an estimate.
Okay, so in an exam now, if they ask us for the estimate, we will leave it as the
It's a good question. I don't write the exams, so this is me giving you my best answer.
Okay.
My best answer is if they have a range, give them a range.
Mm-hmm.
And if they have a single number, do the average.
Okay.
Not like one of the large ones or one of the small ones. If they say, what is an estimate? And they only give you single numbers, and like part A is answering this, B is this, and C is this, pick C.
Okay.
Because it'll be closer to C than A or B, most likely. Well, yes, it will be closer to C than A or B. So, yes, that is what you do here. So that is all conceptually definite integral stuff. What on earth are they doing in problems 28 or 18 through 25? Just use a calculator or a computer? That seems unnecessary to me, but like should like just have you like use a calculator to solve the problem.
You know, that wasn't part of our questions to do.
Oh, okay.
Like it wasn't. I think it was. These questions were 1 through 21.
Okay, and you guys were just doing the odds. Okay. Let's quick do number 14. So this is on page 254. And we have this graph that kind of looks like this.
All right, hold on before we go to 14.
Oh, yep.
I didn't mean to skip over, but can we either do 5 or 3? Five. 5. That one I was a bit confused with.
Okay. So doing 5 now, we're on page 553. 253. That's the page we're on.
Mm-hmm.
So we are going to do, we have this integral from 0 to 1. You have e to the negative x squared dx. This is another thing. I forget to do the dx a lot, which is very problematic, but the dx is always there. Trust me. Just call me out if it's not there. And we know that n is equal to 5. So we know that we're estimating this using rectangles. Basically what we're going to do is we're going to use the same equation that we were given back here, which is the I is equal to 0. This is all like notation-y stuff, which I personally don't believe in because I think it makes math inaccessible. But it's not really my call. So basically what we're going to do is estimate it given n is equal to 5. And we're going from 0 to 1. So if we were to, for instance, like sketch this out, this is the y-axis, this is the x-axis. Here we are at 0, here we are at 1. So we're going to go by 0.2, 0.4, 0.6, 0.8. So then we have 1, 2, 3, 4, and 5 even pieces. So we're going to have 5 different rectangles, for instance, if we were going to be drawing this. We're not drawing it, but we want to make sure we had even pieces. So n is equal to 5. Another way you can kind of imagine this is like a table, kind of like we just did in problem, what problem was that? It was problem 7. Oh shoot, I did an odd one again. What is this? Okay, sorry. Yeah. In my other class, I need to do the odd ones only, and this one I need to do evens. I need to be better on track of this. Okay. So we can kind of imagine it like a table and say that like x is equal to something, f of x is equal to something, and we start here at 0, we end here at 1, and then we're going to have 0.2, 0.4, 0.6, and 0.8 in these boxes. Right?
Mm-hmm.
And so this is going to be the function. So given that f of x is equal to this, right? Let's fill in the rest of this table. So it starts off as 1. E to the negative 1 is going to be 1 over e. And then it gets more and more messed up between there. Where's my e button? This is 0.52. Sorry, I didn't draw this table very well. This is 0.698. 0.852. And 0.961. Okay. And 1 over e is going to be equal to 3.6. Okay, so I'm going to rewrite some of this stuff over here, just so that we have it like for reference when we're doing the rest of this problem. So what we did was we divided our chunk from 0 to 1 into 5 even pieces. Then we found out what the function for each of these pieces was going to be. So if x is equal to 0.2, we know that f of x is going to be equal to 9.61. 0.4, it's going to be 0.852. Try. This is 0.698. 527.368. Does it make sense, this pattern? As x gets bigger, does it make sense that f of x is getting smaller? Yes, it does make sense. So we're going from 0 to 1. Sorry, I'm just going to rewrite this problem. E to the negative x squared dx. So that is where we're at right now. Let me erase some of this nonsense. So now we have a lot of the information that we need in order to finish up this problem. Basically what we're going to be doing is we're going to be pretending that there's a Riemann sum going on here. And we're doing the left-hand side first. This purple is the equation for left. And what we're going to do is we're going to say that we have all of these sums. And so basically what this means is a lot of things are added together. And what we're doing is we're adding, we're starting with I is equal to 0. So we need f of xi. So the first of our numbers is going to be x is equal to 0. So f of x, or f of 0, times delta x, which in this case is the distance between x values. So this is equal to 0.2. So this is times 0.2. So then we have f of 0.2 times 0.2, f of 0.4 times 0.2, and f of 0.6 times 0.2, plus f of 0.8 times 0.2. So we have 5 different rectangles, 1, 2, 3, 4, 5, and each of them have this area underneath the curve, and we are going to calculate that area to be some number. Are you putting that in the calculator right now? That would be really handy. So, cool. So basically, using the information from here, that's what we're going to put in. So, cool. This is 0.8076. And so that is going to be our estimate for the left-hand sum. We're going to do the exact same thing, but we're going to interpret this equation in the pink for the right-hand sum. And so basically what this is saying is that we need to have f of 0.2 times 0.2 because delta x still equals 0.2. We're using the same graph or the same chart up here. Instead of starting at 0 though, we're starting at 0.2 and we're going to go like this. That's confusing. Okay. So we're going to do that plus f of 0.2 0.4 times 0.2 plus f of 0.6 times 0.2 plus f of 0.8 times 0.2 plus f of 1 times 0.2. So we're going to get that through. Give me a sec. So this should be 0.681. Okay. So that is how you do problem number 5. A few things I will draw your attention to. I'm going to do this in green so it like stands out. Sorry, I'm moving my chat box. Okay. So these equations are very, very similar because this chunk in the middle is all the same. All of this is in each equation. So 0.2 times 0.2, both there. 0.4 times 0.2, f of 0.4 times 0.2, 0.6, 0.8, 0.6, 0.8. What is the difference between these two equations? Well, it is what is on the end here. In this one, we have that, and in this one, we have that term. So it's our starting position and our ending position. And so the difference between these two is whether or not we start at 0 and go through 0.8, or we start at 0.2 and go through 1. So these two equations are very, very similar. The only difference is these two terms, which is why we get this difference. So yeah, any questions regarding this? Cool. I'm gonna clear all of this. Whew. Freedom. And move on to 5.3. So basically, what we're saying here is that the definite integral can be considered like something that my calculus teacher did that I always really thought made sense was that he explained things in terms of like both derivatives and integrals. He said there was always a graphic interpretation and an algebraic. So, for instance, with derivatives, the graphic interpretation was that we were looking at the slope of the tangent line. At the point. We were looking at the instantaneous, and that correlated to the instantaneous rate of change. Algebraically, we were looking at this whole process, like chain rule, product rule. We had this whole set of equations and stuff that we would learn how to do, and we knew that that correlated to the instantaneous rate of change for a point. But the whole thing about finding with derivatives is linking these two concepts and being able to understand that although a problem may be initially posed as an algebraic problem, you can use a graphic tool to solve it. So that was kind of a thing that I really enjoyed from my calculus teacher, which is why I'm bringing it up. So that same principle is going to be used to apply to integrals. So instead of the line tangent to the curve, it's going to be the area under curve. and there will be methods to solve. Did you guys, it's 5.4 is antiderivatives, right?
Mm-hmm.
Cool, okay. Yes. Okay. So, reversal of the derivative, we're looking at area under curve. We have these methods to solve that we're going to be using later on. Another thing is, so I always like to think about things in terms of both like geometry, not geometry, but like the graph and what's happening in like the algebra of it. And in addition, I would point to page 255, figure 5.27 and 5.28. Basically what this is showing you is like how you go from area of rectangles to like the integral. But another thing that I wanted to point out is that they have this curve and it's like doing its thing. And it looks like this, and like there's all of this area shaded in underneath this. And this is a definite integral because it goes from point A to point B. So it's very important that you guys like are capable of like discerning like what a definite integral is in comparison to an indefinite integral when you start catching up with them. Because like it's gonna confuse the heck out of you if like you can't keep them straight. So the reason that this is a definite integral is that it goes from point A to point B. If it was indefinite, it would be everything. All of the area under the curve, every part of the curve. Like the whole thing, the whole graph. And there are instances where that is useful. But a lot of the times they're going to have you problem solving using definite integrals because that gives you more control over the area that you're finding. Does that make sense? Yes, no, maybe so. Cool. Okay. That being said,
I think the most confusing part for me is like when they go to like when you go to the next page, page 256,
yep.
and they have example 2, and you have all these. You look at it like the one where it says interpret the definite integral.
Yeah.
Yeah, and it confused me the whole middle part where the x cubed minus 7x squared plus 11x. It's like all these numbers now. What am I doing?
Okay. The best thing I would say for you is to like break things down into like manageable chunks. If you're looking at this,
I understand why they end up breaking it into 2 halves, but their answers just didn't make much sense to me. But
okay. So you understood why they broke it into halves because of the negative area.
Yes.
Okay, that's good. That's a big concept. What didn't make sense about the answers?
Okay, so when they broke it into 2 halves now, are we looking at just 2 different portions from like 0 and 238? Are we looking at 0, 1 point something, 2, 238? Like, where is it that they come up with this answer for the 7.2? Is it a breakdown of each section?
Okay. So basically what they did is, here, I'm going to redraw this curve so that I can, okay. All right, so this is the curve that we're looking at. We're looking at it between 0 and 4. This dotted line here, that's going to be 4. So here's 0. This is 4. This is going to be
2.38.
2.38, because that's where it's going to equal 0, right?
Mm-hmm.
So that's where our 0 is. So we broke it into these integrals. We broke it into, I'm going to color code these. Does the color coding help?
Yes.
Okay, good. So we have 0 to 2.38 of f of x, and then we have 2.38 to 4f of x, and this curve is going to just be f of x. Basically, like, so they break it into this chunk, and then they're going to do, they say calculating each one separately. So the way that they did that is either using antiderivative, like the methods that you'll be learning in the next few chapters, or they used the sums.
Okay.
So basically what they did is they solved it. And they said this chunk, the area under the curve, this curve from 0 to 2.38, this is going to be equal to 7.72. I'm just going to do it in black or something. Okay. That's really busy. Okay. Okay. Here we go. Okay. Then they were like, okay, so I'm going to find out what this area is using sums or like whatever other method. And they found out that this area is negative 5.05. And the reason it is negative is because it is below this x-axis. So it's counting negatively. So what they did is they said, okay, so basically what you do is if you're trying to find this whole thing, not that. If you're trying to find this, what you're going to do, and you can break it up into whatever you want to do, 0.238 plus 2.384. So basically what we said is that, like, you can break it up into whatever chunk you want. If you want to do it in chunks of, I don't know, like 1, you can do from 0 to 1, plus from 1 to 2. That's like a property of the integral, is that you can divide it out. So I could chop it into however many pieces I like and do whatever I want with this. But as long as I cover every x value, then the answer is always going to be the integral from 0 to 4 of this function is going to be 2.67, right? 67.
Yes.
Okay. And the reason that is because this is counting negatively. So this is going to be 7.72 plus negative 5.05. So what this is doing is basically saying that, okay, so I have this integral that like is going to turn out to be a smaller number, because consider if perhaps this was velocity. If this was velocity, then our derivative graph, we would be looking at, we would be traveling some positive distance, and then we'd be going backwards. So we would have negative velocity. We're going in the opposite direction of the direction we should be going. So I drew that graph really poorly, the green one, so like ignore the fact that I just drew that, because that I don't think will help. But so that is like the general like overview of example 2. I'm going to kind of go off on a little bit of a tangent here and say something about this. So let's not do that. Let's do this. If I can draw a straight line. Okay. So this will be 2, and this is going to be 1. And these numbers are arbitrary. But the point is that these graphs, this graph is going to have the same area. So this area is going to equal, I don't know, how tall is this? This will be 1 tall. So 1/2 base 1 times height 1. So this area is going to be 1/2. This area also equals 1/2, but it's negative. So if we were thinking about this in terms of velocity, we would have like gone up in velocity, and then our velocity would have decreased and decreased and decreased, and then it would be negative. So we'd be going like backwards. It's like we got in our car and we turned around, and so we're doing negative velocity in the opposite direction of the one that we should be doing. And then that velocity like then approaches 0, but we're still backtracking. So that's like one way of like thinking about this. So in all, the integral from 0 to 2 is of this function is going to equal 0, because this area is positive and this one is negative. And so we're adding these two together, a1 plus a2. And so 1/2 minus 1/2, that's going to be 0. So basically, what's going on in this graph is that we have these two chunks that are basically inverses of one another, and they're canceling each other out. So it's like we didn't travel anywhere at all if this was a distance graph. Now let's pretend, for instance, it looks like this. Will we have traveled? Well, this is going to be a1, and this is going to be a2. And a1 is bigger than a2. We can establish that just by looking at it. And a2 is negative. So we know that the addition of a1 plus a2 is going to be positive, because a1 is positive and a2 is negative, and a2 is smaller than a1. So here we have some sort of positive integral. Basically, there are instances, and I can't think of a good one off the top of my head right now, but there are, like at some point in time, they might ask you a question kind of like this, saying that we don't care about the negative integral. We want the area if you pretend this is positive. So if this is 1, this is 2, and this is 0. So we would have this a1. Let's kind of like pretend this is our last graph, so that's going to equal 1/2. And then we have this a2, which is going to equal negative 1/2. But we don't care about the negative sign now, because we're not like traveling a distance, or like there's some other problem, and they specifically stated in the problem that we want the area without the negative signs. So then it would be A1 plus the absolute value of A1 plus the absolute value of A2, which would be 1/2 plus 1/2, which would equal 1. So this area is 1/2, this area is 1/2. If we combine them together without pretending the negative sign is not there, we get 1. And that's why they have you separating it, because at some point in time, the integral, like you may be like asked if like the integral is going to, asked to like find an integral where something is perhaps not like considered negative. But don't worry about that right now. That's just like the reason they had it split up.
Okay.
That's why they did that. Not necessarily because it was the best way to solve it. You can just find the integral from 0 to 4. They just wanted to illustrate the fact that we had to like look at this chunk as positive and this chunk as negative. So, all's good. All right. So you don't need to worry about solving problems like that right now. Those may come later in this class. I don't remember if we did them last year. I don't think we did, but that's the reason that they have it broken up like that. And it's just kind of important to like look at a graph and say, what is the derivative going to be? Is it going to be negative? Is it going to be, or not derivative, excuse me, integral. Is it going to be negative? Is it going to be positive? Like what's going on here? Okay. Is there a problem that you, problem type that you would like to do?
Can we do 4?
Yeah. Sorry. Okay. So we are in section 5.3 on page 258. Doing problem 4. So find the area between y is equal to x plus 5 and y is equal to 2x plus 1 between x equals 0 and x equals 2. So this is having us do the area between two curves. So this is on page 257. We have some equations there. The area between two curves, making sure they're functions, like contiguous functions that we can take integrals from. That would mean that what I would do is I would assign f and g. So this is going to be f of x is equal to y is equal to x plus 5. So we can get rid of that y. Don't have to think about it. G of x is equal to y is equal to 2x plus 1. All right, so now we have our f of x and our g of x, and they're both in terms of x, so that's good. Next, what we would do is we would say, well, I know that I can use this equation that says from a to b, I have f of x minus g of x dx. And this is the area between, which happens to be what we're looking for. So what I'm going to do is I'm going to say from 0 to 2, I want x plus 5, and then I'm going to do minus 2x plus 1 dx. Simplify this out. 0 to 2, we have x plus 5 minus 2x minus 1. Distribute that negative sign, dx. Pull this out using algebra. So it's just going to be negative x plus 4 dx. And so You don't know how to use antiderivatives in this section, do you?
No.
Okay. In which case we would use this using the sums. So we would say we have, like, if we were to like go very, very vague, we would have x f of x. We could do 0. If we were to do very vague, it would be 0, 1, and 2. But that is problematically big. So what we should do is 0.5, 1, 1.5, 2, which is still very, very vague, but not quite as vague. So f of 0 is going to be 4. This is going to be 3. This is going to be 2. This is going to be 2.5 and 3.5. Right?
Mm-hmm.
Okay. So
Yes.
then what we're going to do is we're going to do the whole Riemann sum. We're going to do the left, which is going to be 4 times 0.5 plus 3.5 times 0.5. And then we're going to like work all of this out. I don't know if you want me to go through all of that right now.
No, you don't have to go through all of that. Like that part, I get the idea.
We're just going to use the Riemann sums, and we're going to take the average of that. And that's going to be the area between the curves. Does that make sense?
Yes.
Cool. Awesome. Do you have any more questions about?
No, I think I'm good with that now.
Okay. I only allotted like an hour for tonight.
That's okay.
Was probably problematic.
Mm-hmm.
But if you have any more questions, of course, feel free to email me. Inbox is always open. And like I said, it's like a lot of this is like the conceptual stuff, and it's like important that you understand it so you can solve word problems. So, which are, of course, a favorite of math professors.
Okay.
Who doesn't love word problems? So, that is what's going on.
Okay, yeah, I have a better understanding now of 3.5.
Awesome.
And 3.4 wasn't too bad. It's just building, so that's okay.
Awesome. Okay. Cool. Well, then I am going to let you go for tonight. Have a wonderful evening, and if you don't email me, then I guess I'll see you next week.
All right, thank you.
A good one.
Okay, bye.